Thank you very much, organizer, for inviting me for this nice QCD session. Actually, my background is statistical physics simulation. Therefore, QCD, Lattice QCD simulation is maybe an upper version of my Ising simulation. So I have some sympathy with this field, but unfortunately, I didn't have a chance to get the physics commitment to this field. Before starting to that, I just make a brief announcement or advertisement about the computational physics conference. I and Aoki-san and some of the Japanese computational physicists are planning to host the next or coming CCP conference here in Kobe, maybe in a little bit over there, the International Conference Center. So, and paper submission will be open next month. So I hope you enjoy again here in Kobe. Okay, now let's start my presentation. Maybe I will introduce my background a little bit more. And so maybe this is my first supercomputer I used in my scientific career. So this is so-called Ising machine, the first Japanese Ising Anira. I and Dr. Makoto Taiji collaborated and constructed 2-bit supercomputer simulation guides in United States and also European. That time, I and Makoto was both a master course student. We didn't have a chance, but my supervisor, Masuo Suzuki, he's rather known as a quantum simulation originator, and he had accepted to use $1,000 to make supercomputer simulation. So my university, Tokyo University, was very close to Akihabara, the solid state center of Japan. Therefore, we from time to time go to Akihabara by bicycle and bought some chips and accumulated some board and using wrapping connection, make an Ising model annealing simulator. And nowadays, the Ising annealer is much more fashionable. And the most, in some sense, fashionable Ising annealer is the quantum computer. Maybe at that time, this was a story of the 1980s during my student days. But that time, maybe some railway coming to this position may already be prepared by some people. Okay, another things I encountered this kind of things is the very famous Professor Feynman presentation in Tokyo. That time, Professor Hiroshi Ezawa in Gakushu University that time invited Professor Feynman to give some presentation. That time, I was a student in physics course. I was expected to give some new idea or something new about the quantum electrodynamics or for something more or field theory and so on. But he didn't talk about that. He talked about the future of computer. And this booklet I got after that. So that was the first time I get the idea, what is a quantum computer? Actually, I didn't have a good idea what is a quantum computer at that time. But anyway, he gave us a very nice idea why quantum computer or quantum process or quantum dynamics using unitary dynamics for the computational purpose is very important. First of all, energetic sense. Secondly, some algorithmic performances, and maybe Deutsch and Shor and as some other quantum algorithms followed during the 1980s, and finally we are reaching this position. But that time we still are skeptical about whether really we can control such quantum processes, very, very fragile entities in 1980s. But now in this 21st century, quantum mechanics is not just some idea to understand the nanoscopic world, but we can really control it, and not only the nanoscopic world, but also a little larger than that. Mesoscopic scale quantum field, quantum effect is also observable. Okay, so, but that time in this sorry, I feel a little bit hot. Remove my. So, but the first quantum bit qubit was realized experimentally in 1999, and that was just 1 qubit, and that was a very nice achievement by Professor Nakamura, now the director of the Quantum Computer Center of RIKEN. And that time, stationary saw something like that. Therefore, just one qubit and only very, very short coherence time or operation times. Therefore, maybe we can just simulate that to elucidate what kind of application we can expect for the quantum computer. Maybe just using the computer simulation of the quantum computer, that will be okay. Okay, that is not only me, but some other project started. Some other people also think something like that and started some national-wide project of the Soumsho project about the quantum telecommunication, quantum information. That is the story of the 2003, something like that. And okay. So maybe we can just make the very brute force simulation. We now call the state vector method or algorithm. That is nothing but just make the qubit 0 and 1 and that as a complex superposition of that. You simulate that amplitude. If here is n qubit, we prepare the 2 to n complex numbers and operate. That's very simple. But using that, maybe in the beginning of this century, maybe we cannot expect so very nice future. Maybe we need exponentially large resources to get more qubit. But maybe we can do we could do something using some quantum Monte Carlo algorithms or some others. So that was our first challenge, but it was in vain finally. So that was some trial. So each gate, so you have some sense. So each horizontal line from left to right, time goes on, and each marks that corresponding to the unitary operation operating on the qubit or lines connected on this diagram. And each qubit is nothing but a 0 or 1 superposition of that, complex superposition of that. That is something like that. The spin systems, spin 1/2 system. So, and this is one of the very famous historical circuit. That is some simplification of the Shor algorithms. That is a kind of some prime decomposition algorithms. But anyway, something. And after that, something good is expected. Okay, just believe me. And so instead of just making the 2 to this number of Hilbert space operation, but making some each operation gate is make some localized or classical approximate transcription, just using some tricks. Here we use the Hubbard-Strauss transformation. That if two spin operator SS is productly coupled, then we can replace that using some 0 or 1 auxiliary field, something like that. Such kind of things was already established in the electron simulation, Hubbard model simulation. That time we applied. Anyway, it's converging. So here is many representation after all in average. So here is the simulation, Monte Carlo simulation dynamics. So the horizontal dashed line, the exactly expected numbers, it is really around that after the averaging over it works. And maybe we can do something similar to the Fourier transformation. In that case, another Hubbard-Strauss transformation, this phase shift operator is transcribed using some C number N1, N2, and it's really converging to that. Okay, it works, but not only that, sorry, on this screen it is a little bit strange. I have to remove it. Okay, and not only that, we also needed to some application or software to make this kind of drawing or operation much easier. Instead of just using some graphic things, maybe we make up some computer-assisted design system, CAD. Not only the CAD system, but also some state vector simulation behind that. It worked on the Windows systems, and that was also developed. That time, the number of qubits is limited only to 7, 8, 9, at most 10 or something like that. But anyway, and this kind of things was the first challenge, very, very primitive challenge, started in the beginning of this century. So after that, we realized, actually, in the first impression, state vector simulation was very expensive. But now we have the supercomputer, very, very massive parallel supercomputer, where it seems to be developing very highly. Okay, the supercomputer situation in the beginning of this century, a little bit turning point. Before that, some vector process or some processors have a processor at most 8 or 16, that vector processor complex. That was a state of art in the 1990s. Of course, connection machine existed, but it was a performance a little bit behind that, even the connection CM5 machine. But we had very big vector parallel machine in 2003 and 4. That was the Earth simulator, achieving 40 teraflops, very, very big performance that time. And then using such more than 6,000 processors, vector processors, we can tackle many, many bits like 20, 30, 40 qubit seems to be feasible. Therefore, we changed our attitude. So not trying to make some nasty tricks to simulate the quantum circuit, but just to make brute force state vector simulation. Okay, so this was the first world record we achieved in 2007, using the blue jeans queue that time in Yuri, and also Japanese supercomputer in Tokyo University and some others. But anyway, that time we simulated up to 36 qubit. So 36 qubit means that we needed to treat 1 terabyte double precision complex number. 1 terabyte was very, very big that time. And almost more, after that, almost 11, actually it was 12 years later, and also we tried another simulation using the K computer, previous supercomputer in our site, and reaching to the 48 qubit. And actually 48 is using the byte precision 48. But the double precision, we touched 45 qubit. That was a story a few years ago. And then 2020, this decade, quantum computer seems to be more fashionable nowadays. And not only just a very, very primitive quantum computer, 10 qubit or 20 qubit, but also 50 Google machine and so 100 IBM machine is now coming. And of course, the reliability or so-called the decoherence time is not so big. Therefore, after the hundreds of operations, the quantum coherence destroys nowadays. And now IBM is trying to make the 133 qubit chips and more than 400 chips with higher reliability. But anyway, those things we need we start to think about what is a good usage of those things. And we have some hope in near future means 10, 20 years from now on, a better quantum computer will be available, very reliable. Maybe one target is 1 million gate, 1 million qubit, and operated 1 million times or more. That is what we expected in near or middle future. But anyway, on the way, we need reliable quantum computer operation understanding for the purpose. The state vector simulator is very reliable. And another idea is trying to make so-called the tensor network, you may know. So maybe the quantum circuit that is cut in some places in which we make some trace out using the classical computer and some blocks. Maybe we have some idea that the so-called entanglement entropy that measures the entropy, measures the degree of quantum coherence or entanglement. And if that is proportional to the circuit area, then we can cut the network rather safely. But if it is much more complicated entanglement network, we do not have a good idea how to tame that. Anyway, the starting point of such simulation, state vector simulation, it's brute force, looks very simple, and it's very reliable starting point to go something more. So we put much more concentration on the development of this simulator. And so here is this will give you some sense what is the quantum code, quantum programming. So here is a circuit diagram as I described previously. Each square H denotes Adamar operation, that is the 2x2 element operator, and a unitary operator, and many shift operator, some control node, something like that. Those are described like this. So here's the C not operation, controlled not operation to the qubit 0 and 3. This is, you may get some sense if you are familiar with assembler languages. Well, maybe the machine language is more primitive things. And this kind of coding, we call it the quantum assembler QASM. And there are several different standards of the QASMs, IBM standard or some others. But anyway, more or less similar things. Some operation and target qubit number, something like this. So here is actually the error correction, simplest error correction code. So here is some X gate. That is something mimic the random noise. And the quantum coherence or quantum state is randomized using random number here. And then, but this qubit information is already have some influence to other qubit, and finally it is recovered after appropriate. Of course, this error correction is not perfect, but anyway, this kind of things can be described something like this. So now here is many simulator, IBM as I mentioned, or many NVIDIA and so on. Not only this QASM level, but also some a little bit higher languages, and that is already existing. And but anyway, those software libraries or languages needed some machines or computer to realize that execution. Maybe IBM qubit, real qubit. We call it the quantum processor unit, QPU. And also the computer simulation, many other things is behind those language software systems. Okay, just one thing. So most important things is to treat a huge number of complex numbers. Operation is very simple. Just operate block 2 by 2 or 4 by 4 or at most 8 by 8 matrices. It's very easy. Therefore, most important things is to tame big numbers as efficient as possible. So it's very simple. Here is L, sorry, now here is the number of qubits is represented by L. And 2 to L state, a complex coefficient, is, and this is a vector space of the qubit quantum computer. And store this 2 to L complex number is important. It looks like this. So, and for 10 qubit case, and then 2 to n is 1024. And each complex double precision number requires a 16-bit. Therefore, totally necessary memory size is 16 kilobyte. Okay, if add 10 more, kilo is upgraded to mega, 30 then giga, and 40 tera. And to simulate the 40 qubit, okay, we can just prepare 16 terabyte. It doesn't look very big. Maybe some hard disks here, we can store 16 terabyte easily. But anyway, the performance is very slow. You can imagine that hard disk latency is very long. And we are now talking about 45 or 48, something like this. Therefore, the K computer case, we reached this number using the half petabyte memory storage. And the Fugak computer, it has totally 2.some petabyte. Therefore, we can, theoretically speaking, we can reach 48 qubit double precision simulation. And actually, our simulator, we named bracket framework for the quantum computer, but that can touch this number. Unfortunately, we didn't test this full performance because this full node operation on this Fugak computer is very limited, and we didn't have a chance to do that. And due to some number theoretic limitation, we exactly need the full number node to realize this performance. But anyway, the 40 qubit or 46 qubit simulation, 45, 6 qubit simulation is not very hard. But anyway, this is the current status of art. And here's some important performance comparison. So K processor, previous machine, it has each node has the 64 gigabyte per second memory CPU core bandwidth. But Fugak computer cases, it is much faster than K computer because K computer has the DDR memory outside of the CPU chips. But Fugak has a high bandwidth memory unit like the GPU. On the chip, inside this chip, here is a stack of memory. And each has the 8 gigabyte times 4 banks, totally 32 gigabyte memory, and 2 core. it has a 1 terabyte per second read-write performance. It has a very big advantage, more than 10 times faster. Not only the in-node performance, but also the inter-node. Then inter-node performance seems to be rather similar, but anyway, a little bit achievement. And the full system, in-node total performance is more than 100 petabyte data treating in-node memory. And also inter-node cases, and it has, we can treat 6 petabytes per second. So if we use the Fugak computer very efficiently, every second we can shuffle this 4 petabyte memory data size and so on. Therefore, we can expect that every second we can update the next stage of the quantum situation, quantum vector situation. So this number chart tell you something more. So if we use the notebook computer or some local CPU that may be using the so-called DDR type memories, the memory bandwidth will be at most several tens of gigabytes per second from the memory to CPU cores. In that case, then around here, at most 30 or 30 some qubit number is the efficient limit. Efficient means, I mean that one operation per second, roughly speaking. And then using the single processor, we can touch around here 30. And we can use the GPU. GPU has like the Fugaku's in-node. We can touch a little bit more, but usually the GPU has less than 100 gigabyte. Therefore, the available qubit will be around again 30 something. So, but as I mentioned, the big supercomputer like this, memory bandwidth is very big. Therefore, we can treat much more than that. Okay, I skip the Fugak things. I do not go to the detail. You may already know about that. Okay, one exotic application with the Fugak big data bandwidth. So this is the GPS data tracking analysis. I conducted 2 years ago as the first stage of the Fugak computer. And this is for the for COVID-19 spreading simulation data analysis. Anyway, each dot has the GPS data collected to your mobile phone terminal. Of course, it is some allowance for the user side. And totally more than 100 terabyte data. And the total record is about 400 to 500 billion record was accumulated in this more than 100 terabyte data. But 100 terabyte from the vendor data holder to here, that takes actually almost 1 month using the networks because they use the Google cloud to keep that data, and they didn't accept it to put the hardware, connect the hard disks to that. So I needed to use the internet connection to get the data, and took 1 month actually. But once the data comes to the local storage here, then the Fugaku is connected to the so-called Fujitsu exabyte storage systems. Total performance can reach the 1 terabyte per second. Unfortunately, my data mining code didn't reach that peak performance. But anyway, within the half an hour, that means about 2,000 seconds, I can load all that more than 100 terabyte data and making some data mining, graph mining to find some connectivity analysis. And finally, we get some, only here I plotted only the tracks. But each point we can identify which terminals are, or more saying, which one is in these places and moving to at what time, something like that. Okay, this is all very interesting pictures already, and we learn something more. But anyway, I do not go to the details. So here is some not only the Japanese domestic traffic or city structure. So if you magnify here, every train systems we can reach, we can see with higher resolution, not only the Japanese territories, but also the Taiwan, China, many other countries' systems also included, except North Korea. Okay, this performance will give you some sense why Fugak computer is so suitable to simulate the state vector quantum computer simulation. So the idea is very simple. So each node, it has some number of complex numbers, coefficient. Another node have the rest of some other things, and that continues. And maybe you can just imagine, okay, here is the 2 to n complex numbers. If we multiply some matrices, necessary coefficient is loaded and make some operation and return back the original position. Okay, that works. But to read and write back, I found a bit abuse of the performance. Okay, trying to just read and without write back. If it is possible, we can reduce the transfer time half. So it is available using a little bit nasty algorithms. So, okay, just example. Here is only 2 coefficient. And let's say here is, then if we needed to operate some matrices to this half data with this half data. In this sense, maybe instead of just transfer and write back, instead of write back, maybe just keep the result here and stay here, and we regarded that this data is always stay here. This kind of things will reduce the write back effort. And a little bit tricky system things, and we need a little bit thinking to implement properly. But actually, it is very easy. And performance or necessary transfer rate is usually half of the total coefficient. Therefore, as I mentioned, for 4 petabyte data transfer and 4 petabyte data coefficient, then every times at most we need 2 petabyte shuffling inside the node. Okay, this is the case for the 1 qubit operation. That is a single qubit Adamar 2x2 or something like this. But CNOT 2 qubit cases, 3/4 data is at most shuffled. And TOF3 or 3 qubit cases, 7/8 is necessary. But anyway, that is so far most efficient way to shuffle the data or implement state vector. Okay, that's all. Here is some description, but time is limited. I do not go to the very real detail for multiprocessor machines, but going to the performance result. This is a little bit old things. The previous one, using the K computer. K computer performance is represented by this blue boxes. And not only the K computer, but IBM Blue Gene Q, Yuquin in the Yulich. And also somewhere Taifu Light, that is Chinese supercomputer, #1 machine at that time. That time means 2090. And then increasing the number of qubits simulated. And so here is the averaged operation time per one single qubit gate. Actually, we call it the Adamar benchmark. And we make each qubit successively apply the single qubit Adamar gate and repeat it 11 times and measure the total performance, and that is reduced with the total number of gate operation. That kind of standard existed. But anyway, so, and if we increase the number of qubits, every time 2 times more data is treated and using the 2 times more CPU node. So this is a weak scaling. And this vertical axis shows the performance change compared to the performance of each machine's 32 qubit case. So that means for K, okay, let's say K computer case, so around up to almost 40, 41 around here, maybe less than 2 times more performance elapsed time needed for the compared to the 32 qubit. And maybe in the very end, using the almost full node, using the 2 to 16, more than 65,000 node, maybe the data transfer is a little bit tangled inside the node and takes more time. But anyway, around here, it is 5 times or 6 times more and elapsed compared to the very small qubit cases. And another machine like Chinese Taifu Light cases, performance is quite linear, even to the very largest end. But anyway, weak scaling is more or less similar with each other, but the unit time is a little bit different. So K computer cases, so one in this K this vertical unit 1 corresponding to the 1 second of the K-computer elapsed time. Euclid case almost the same, 1.2 seconds. And the Chinese machine case, the 1 means 7.7. It's 7 times slower. But anyway, and this is a weak scaling. We could reach the 45 qubit in double precision. And the total average simulation time is about several seconds. 1, 2, 3. In the worst case is 6 seconds. That was the performance we expect. That is what we expected. So, okay, a little bit more complicated things, but I skip the more details. But anyway, so this is the K performance. Just concentrate on this left figures now. And you will see that for the starting from the 31 qubit simulation, reaching to the 46 qubit simulation. So there are several curves. And instead of the difference is how much coefficient is stored in each node. The simplest implementation is limited only for the 2 to n on each node. And we need 2 to n node to achieve the simulation. But that 2 to some number, that integral limitation is a little bit tricky. And we wanted to use up the memory storage of each node and the flux system. Therefore, we make a little bit packed, more packed algorithms implementation. And for the simplest implementation, so okay, here is some situation that the FGA computer cases, we can reach almost 60,000 node parallel simulation every once a month. But more than that, we needed some special preparation and special permission. Therefore, performance is limited to the case about less than 60,000 node about. So, so then the naive cases, 2 to n algorithm case, we could reach the 2 to 15 node simulation using this number of nodes to simulate the 45 qubit with this per gate elapsed time. So vertical axis here, this is just a second elapsed time. And a little bit packed way, we can reach the 46 qubit using the about 50,000 node. And in the end, it really took about 3 seconds. But anyway, a 64 qubit double precision is achieved using this number of nodes. And another packing method. It's a very bad pack. This is a bad example, so just forget about that. But anyway, we can reach the same 45 qubit using about 30% smaller number of nodes. And that is some improvement with the more same performance. So this is what we achieved. And this is for the double precision. Of course, we can simulate using the single precision and complex numbers. So double precision means that there is a 70-digit mantissa. Therefore, we can say, repeat the even the worst cases, rounding errors accumulated after the 10 to 17 operation. But actually, the quantum algorithm so much depth. We call it the depth for the how many operation is applied to each qubit. That so much 10 to 70 depth circuit is not yet tested or considered. Therefore, usually the single precision is that still have the mantissa 6 or 7 digits. That's very sufficient. And but that seems to be still something very more than necessary in case of quantum learning or some other application. So in this case, we can limit the precision more, just half byte using 4 bytes for each complex, or single byte or byte precision using 2 bytes for the one complex number. In that case, we can reach every time 1 qubit more because the data size is half. And then we can finally reaching the 51 qubit for the byte precision. That is the performance we can expect if we use up the FGA computer. Okay, that is the top end. But anyway, good news is that now, as I mentioned, using the workstation or GPU, single GPU or single workstation, or some multi-CPU using a poor network connection, we can, our simulation is limited up to 30 or 32. But if we use a FGA computer using 1,000 nodes is a tiny chunk of the FGA computer. And the 40 qubit is very easy, 1,024 nodes. It's very easy things, and simulation performance is very good. Therefore, this will help the development of the real quantum computer or quantum algorithm. Okay, here is some very complicated summary, but I already talked about that. And data allocation optimization, this is another tiny tricks. Maybe it's not necessary to touch here, but I better to show you some example. So here's the example, application example. There are a wide variety of examples, but nowadays the very promising first example of the application of the quantum computer, many people vaguely consider that maybe quantum variational algorithm or quantum variational eigensolver that is applied to simulate the quantum many-body systems. Like the maybe Quark or QCD will be also be included, and you may know much more than me. But or the molecular design or drug design, that kind of thing seems to be the most promising, most profitable quantum computer application nowadays. So as the first step, we tried one quantum systems. That is a very simple Heisenberg chain. And this is a variational calculation. And starting, we prepare a variation using several variation parameters using quantum circuit, some spin in this case, some Heisenberg spin chain, then using that number of qubit and modified with shift, phase shift, some other things, appropriately prepared parameter space, instead of making some approximate classical wave function, but also quantum mechanical wave function is prepared from some qubit systems. And not only that, for the optimization purpose, we need some derivative of the some physical quantity, or actually energy derivative with the variational parameters. So we prepare the many parameter, a little bit different parameters, and make the numerical or analytical derivative, partial derivative of that. So in this case, let's say here is the 34 case. That is 34 Heisenberg chain, Heisenberg isotropic interaction, exchange interaction cases. And the 34 cases using 34 qubit systems and 34 variational parameters. And this variational wave function is prepared, repeated 34 times of this phase shift operation using the different 34 variational parameters. And here's 34 plus 1, 35 parameters. And the original one, a little bit modified one. And taking the numerical, taking the derivative, to estimate the derivative of that, making some quantum mechanical evaluation using the Hamiltonian of the systems. And with the first system to the second, and first system to the third, and third one to the fifth, and something like that. So totally 34 times 34 matrices is evaluated. And using that information, we select using the steepest descent or some other optimization to minimize the energy eigenvalues, and repeated this operation. And this optimization part is done in the CPU classical operation, and the quantum mechanical part is using this quantum computer simulator. And here is one result. So for this violet curves show you the convergence speed of the energy. It reaching to the ground state energy. And actually this variational function is not very well selected, but not very well selected. Therefore, here is a few percent deviation in the final convergence. But anyway, it is expected that we apply this quantum variational algorithm to this system. Actually, previous study was limited to the 17 or 18 Heisenberg systems, and we can extend it to the 40 qubit. It's still just several steps, but anyway, we wanted to see really it works. And 36, 38, it seems to be very promising. Therefore, our simulator seems to be helpful to design this kind of things already. And so this system, and just the beginning of the 40 qubit, 40 Heisenberg chain simulation, we treated 40 qubit systems, 41 40 qubit systems. So totally 1,640 qubit is treated exactly. And not only just parallelly used, but also finally quantum mechanical expectation value is evaluated using the different 40 qubit. Therefore, more than 1,000 qubit can be treated using Fugger computer for appropriate quantum circuit. Okay, now my time is finishing. So I summarize. Maybe I don't need to summarize with my word. But anyway, we can reach a very, very useful number of qubits, quite competitive with the real QPU. Okay, now this is a very good point. Now here in Japan, our simulator, so this is the collaborator, Naoki Yoshioka, developed this simulator, bracket. Actually, recently, Amazon also announced the quantum computer simulation code named same name, bracket. Maybe they took our name, I believe. But anyway, this is our bracket in this GitHub of the Naoki Yoshioka. And it is a free code and C++. You can use it in your computer rather easily. Okay, now here in Japan, our simulation, not only me, but some other people also are involved in it, in this project. The Japan's simulation technology and big supercomputer. And also Nakamura-san or some other real QPU technology people is also in RIKEN. So we are now trying to wrap up these things all. Not only just making the qubit chips, not only the supercomputer simulation, but also trying to mix with each other and trying to make some testing bed for the quantum computer and quantum computation. And IBM Q, the 27 qubit system is operated in Kawasaki near Tokyo. And we are now hope to introduce a 133 qubit system here in Fugak Center and collaboration with many other companies. And we already started this project, and many software, the quantum something, not only our developed code, but also vendor side supported freeware that is now trying to implement it on the Fugak computer. And the target is not only the real QPU, but also simulator, including our bracket simulator. So this is the state of art nowadays. Thank you very much for your attention.